And can y'all hear me, I guess? There's not too many of you, but all right. Okay, so there will be no vector stuff, interestingly enough. That's the first semester I've seen that happen. But we will be looking at integration by parts, trig function integrals, trig sub, and improper integrals. I think that pretty much covers chapter 7, right? Okay. So let's start with integration by parts, unless you have any questions at the moment. That's going to be not comfortable. There we go. Okay, so integration by parts. Of course, the big idea is that you have an integral where it's not simple enough to maybe use substitution. So you partition your integral into a u and a differential dv and apply this formula. It's really the product rule for antiderivatives, but and hopefully the integral, and so you got to choose your parts, of course, your u and your dv, and then you have to get all the parts by computing du and anti-differentiating dv to get v. Okay, and then you have all your parts, you plug it in, and we hope that the integral on the other side of that formula is either simpler or just not more complicated. Right? And does anybody recall the, I forget the acronym you used to, as a guideline, as a mnemonic to help you out choosing U?
V8.
Is there a way to say that? I don't even, latte or something? We used to say I late, but now it's lie. I don't know. And of course the L is log. I is inverse trig. And algebraic for A, and that just means polynomial stuff, maybe square roots, polynomials. T is for trig, and finally exponential. Okay, and this is the order of precedence for choosing your U. Okay, if you're using integration by parts, it doesn't always work, but I think it'll be sufficient for the exam. Okay. And so let's just start with I guess, the easy enough one. I'm sure you've seen something like this. So according to our latte acronym, what should our U be? Well, first of all, I should say that maybe even if you use substitution first, you'd still use integration by parts, because you would need to use integration by parts for arctangent of U. Right? But what would an integration by parts formula, what would you choose U to be? Yeah. Is there a log? Nope. Is there an inverse trig? Yes. Arctangent is an inverse trig function. Right, so we choose U to be the arctangent. And dv is just whatever remains, and it's a differential, so don't leave out that dx. And then compute the rest of the parts. You're going to need a du. So derivative of arctangent is 1 over the argument squared plus 1. And then, of course, chain rule. We need to differentiate the inside with respect to x. And v is simple enough. We know how to anti-differentiate x dx. So half of x squared up to a constant. So then you would apply your formula, right? We have u times v. So I guess we can think of it as u times v. and then minus the antiderivative of v times v times du. So we're going to get, conveniently, some stuff will cancel. And I think from here on, it's a simple substitution after tidying this up. Let me actually bring that over here. So I think we're going to get an x cubed divided by x to the fourth plus 1. Conveniently, that's good enough for a substitution. Okay. Of course, that doesn't always happen. At times, we have to use integration by parts more than once. So this would be like a quarter of a log. And I'm technically put in the absolute value bars, but I guess we all know that we don't need them in this case, right? They're all redundant. X to the fourth plus 1 is positive. Right, so that was just a simple, gentle introduction. Okay. Maybe an example of where you need to use integration by parts more than once. And tell me if I'm moving too fast or if you need to copy anything down. I guess it would be anything like a polynomial times some exponential. And we can make the polynomial, oops. If you want to use integration by parts more than once, we can make the polynomial, let's say, squared. So we'd say x squared minus 5, right? E to the 3x. Right, so we do have an algebraic part. That would be the polynomial. And we do have an exponential. So we're going to choose u to be the algebraic part. I hope that makes sense, because when you choose u, you compute the derivative to get du, and that reduces the exponent to the power by 1 of the polynomial. So hopefully, eventually, you get a simple enough integral. So we're going to choose u to be x squared minus 5. dv is whatever remains, namely the exponential times dx. Differentiate u to get du, and anti-differentiate dv to get v. Okay. And then we can use our parts formula. So that would be u times v minus, so u times v minus the antiderivative of v du. Okay. But I just wanted to have that simple lesson that this integral that you get on the right-hand side of the integration by parts formula is simpler, but it's still not simple enough, right? So we're going to have to use integration by parts again. So forget this is not a touch screen. So we're going to use another integration by parts on this guy. And that's supposed to be blue, not rainbow, but that's okay. And we have the same situation, right? We have a polynomial part. Let's change that. Okay. We have a polynomial part. In fact, we can probably bring out the 2/3 outside to make things easier to write. I'm just going to take out the 2/3 and just worry about the antiderivative of x times e to the 3x for now. And we're just applying integration by parts again, where we have polynomial x and exponential e to the 3x. Take the derivative and antiderivative. Okay. And for engineers, later on, I think you will learn that the more efficient tabular method for when you have a polynomial times exponential. But anyway, we apply integration by parts, so u times v minus antiderivative of v du. Except this time, and then the v du. Right, so we have 1/3, which we bring in outside the integral. And now our integral is simple enough just to anti-differentiate. And I'll go ahead and distribute the 2/3 into the brackets here. And watch out for those double negatives with integration by parts here, right? Because you'll get a minus from using integration by parts once, and another minus per formula from using integration by parts another time. And so you'll get a negative of a negative, so. And what's the antiderivative of E3? Yeah. Up to a constant. It turns out that you can always kind of like polynomial times exponential. That exponential always reproduces itself, right? So you can just factor that out, especially when plugging in the bounds of integration. That way you don't have to play plugging in the bounds into the exponential function over and over. Just factor it out, and then you'll be left with a polynomial here. I'm not going to bother trying to simplify this up to a constant. Okay. So polynomial and exponential, use the polynomial, and then you use integration by parts many times until the polynomial reduces to a constant. And then you have an easy integral. Okay. Now, another time you'll be using integration by parts. It's very similar to, okay, can I move on? Okay. And I am recording this, even though not on my usual platform of e-learning Blackboard, so hopefully it'll be okay. Hopefully I can download this and put it on YouTube. So another time you might use integration by parts is if you have a polynomial times sine or cosine. And it's exactly the same procedure as exponential. It's the same thing. Right? So I'll probably won't do this one just for the sake of time, but you can try to practice. What is it? Second degree polynomial times, let's say, sine of, make it really easy, x. Again, we have an algebraic part which precedes the trig part in our acronym, helping us decide what u is. So apparently u should be the polynomial once again. And we're gonna, well, you know what? I'm just going to use tabular method really quick. So that would be minus cosine x minus sine x. Just so that you can practice this one. It's exactly the same idea as the previous problem. But you would get u times v minus, according to the formula, v times v times v. And then plus 2 times cosine up to a constant. And so you can try to simplify this, but there's an answer if you want to practice. I just wanted to mention that you might see polynomial times trig function. Okay. All right. Now we also want to deal with logs. So we're going to do maybe one where, well, no, okay. Okay, would we need to use, we're not doing this one, but would we need to use integration by parts here? No, and why not? Just really quickly. Because what kind of integration technique is sufficient here? U sub, right? We see that the derivative of log x is 1 over x, and we see that in the integral, right? So there's no reason to use integration by parts, even though you could probably try it, but we won't. Okay, so instead we're gonna, right? So if you don't need to, you know, if substitution is sufficient, don't use integration by parts. But let's try something like this really quick. Okay. So here, even if we use substitution for like u equals 1 plus x squared, we still get the antiderivative of log of u du. But you would need to use integration by parts. So let's just go ahead and try integration by parts. So what should our u be according to this acronym, latte? It looks like log comes first. And it makes sense if that's our u, and algebraic is next. If that's our u, the fun thing about log functions, you know, log function is a transcendental function. But if you differentiate, it becomes rational. So we have more techniques for integrating rational functions, right? And then dv is just whatever remains. So if this is our u, dv, it must be the 2x times dx. Okay, so then we compute the rest of the parts in order to plug into our parts formula. And don't forget the chain rule, the derivative of log is 1 over whatever's sitting inside the log in the chain rule, right? And v would be x squared. Okay, so then we plug in our parts, we get u times v. U times v becomes x squared log minus the antiderivative of v du. So it becomes 2x cubed. And now, so this is now a rational function that you want to integrate here. And so the method for integrating rational functions, one of the methods, right, you learned is partial fraction decomposition, which is later on. But here we wouldn't use partial fraction decomposition. Can anybody tell me why? Or at least not immediately. Why wouldn't we use partial fraction decomposition on this rational function?
Isn't it because the numerator's like degree is greater than the denominator?
Yeah. Oh, well, that too. Yeah, you can't factor the denominator. But yeah, you're right. I wasn't thinking. But it's just that you can't use partial fractions until you have the polynomial in the numerator has to be a smaller degree than the polynomial in the denominator, right? So you, yeah. the degree in the numerator is 3. The degree in the denominator is 2. We can't use partial fractions, and we would need to anyway. So what do we do instead?
We'd have
What
to
do you do
divide
when
it
you
out.
have a polynomial on top, which is the same degree or higher than the polynomial on bottom? That's right. So we need to divide the smaller degree polynomial into the higher degree polynomial in this case. So I'm just going to factor out the 2. And then we're dividing x cubed by x squared plus 1. And we just look at the highest powered terms to decide what to do, right? So we look at the x squared over here and the x cubed over here. And I guess what times x squared gives you x cubed? Yeah, x. You can also think of it as just you're dividing x cubed by x squared, so you get x, and that's what you get, just x. And then you multiply through. So you might need to review long division of polynomials if you haven't already. And you get minus x. Okay. And so we know to stop, right? So apparently x cubed divided by x squared plus 1 is the quotient. And then plus the remainder divided by the divisor. So does anybody want to see how, get reminded how that works after you do long division? You get the whole number part, so to speak. It's the quotient part. And then plus, and then you just write down the remainder divided by whatever the divisor was. Okay. All right. Okay, so this rational function can be simplified as x minus x divided by x squared plus 1. Yeah, so this kind of integration by parts with the log is a good place to also test you, like for partial fraction decomposition on the other side, right? Kind of a double jeopardy type of thing. All right, and then we anti-differentiate x. And does anybody have enough experience to tell me what this antiderivative is? Or what technique would you use to figure out what the antiderivative of x divided by x squared plus 1 is? U sub, right? Because the top is 1 degree less. So you just lump the 2 terms in the denominator into a u, du. So now we see that the denominator is u, right? And the numerator x dx is half of du. So you get half of du over u. So you get a log. The anti-differentiate. Well, anyway, you get minus and then half log, and I'm just going to leave the absolute value off because it's positive anyway, up to a constant. And I guess you can simplify by distributing as well. Okay. This is too similar. All right. I'll post the problems along with the video. I'll post the link to the problems in the description of the video, assuming the video will exist. Okay, so what do you think? For integration by parts. You can help me out, choose U, and then choose dv. Well, I mean, just what's your intuitive guess about what U should be here? Maybe, I haven't tried that. That's not what came to my mind, but sine of X could be. I haven't tried that. I'll try that. Do you mind if I try that later? Right, because the reason I wouldn't be trying this is because to get V, I would have to use integration by parts. Which is, so it's viable. I think it's viable. I just wouldn't try that because instead I would say, well, you know, we have this algebraic part, and when I compute du, it just kind of, you know, you lose a degree, so you just get dx. And the dv part, well, we can easily anti-differentiate dv because there's like a u sub coming there, right? You have a sine and a cosine. And we know that the derivative of sine, say, is cosine. So that's ripe for a u substitution, except I won't call it u substitution. I'll just call it z substitution or something. I don't want to double use u. Right. So this becomes z, and cosine x dx is just easy. So you get half of z squared. Or, oops, sine. Okay. So then we have all our parts. We have u times v minus the antiderivative ddu. V du. Okay. And from the section that's coming up, and the one that involves integrals with trig functions, how do we deal with, I'll try this later. Okay, can I just delete? Okay.
I have a question.
Does anybody remember how to deal with when you have sines and cosines, but all the powers are even, what identities you need to use? Yeah. So if you have sines and cosines, right, and you have even powers for both, you might need to use an identity or two.
Less.
I think they're called power reducing identities. You might need to use it over and over. In this case, it's simple enough. It's we have sine squared, so we know that's equivalent to half minus a half of cosine double the angle. So it's a trade-off, right? You reduce the power, but you have to double the angle. All right. And then that antiderivative is easy enough. I believe you get half of x. And then cosine, what's the antiderivative of cosine 2x? Okay, so, and we have a half in front. So you're going to get a quarter of sine 2x at the end of the day. So let me make sure we write that clearly. distributing. Okay. Good enough. Do you guys want to see an example of cyclic integration by parts? Do you know what I mean? Does anybody know what I mean by cyclic integration by parts?
Less.
So we might try a really simple one, but something like, and this is important for if you're into engineering and stuff, but something like this, right? Where you have an exponential and a trig function. Really doesn't matter what you choose u to be or dv to be in this case. If you'd like, you can just go along with the acronym latte. Trig and then exponential. Okay. Another one where you can use what we call cyclic integration by parts. So I'm trying to decide which one would be a little better for us to do. Here's another classic. Okay, so which one do we want to do? Well, let's try a really simple one of the first type. Just in case. Or, let's actually do B first. Okay, we'll do this one first. Really, there's not much choice here if you're going to use integration by parts for what u should be and what dv should be. So what should u be? Yeah, I'll try to slow down. I'm sorry. Well, you know, you have to choose dv, right? So that you know how to anti-differentiate in order to find v. So if we choose this to be dv, that makes no sense because it's just the original integral to find v. Okay. So it seems to me like, okay, one of these buttons is an eraser, right? Okay, well, never mind.
Why can't we do u sub? Why can't we just do u sub?
U sub for the cosine of log x.
Yeah.
What would you let u be?
ln x.
But if you choose in a substitution, if you choose u to be log, when you compute du, you get a 1 over x, and we don't have a 1 over x in there, so I don't think that's viable. So we just let u be, well, this thing, right? And then, I mean, we can definitely differentiate this. It's easier than anti-differentiating. And then dv is just whatever remains, so that must be the dx. So du would be well, the antiderivative of the derivative of cosine. Chain rule, so derivative of log dx. And v would just be x. Okay. So we apply our parts formula. We get u times v. Okay. Minus the antiderivative of v times du. So that looks like the x's cancel. Let me just write it out. Okay, so we do have some nice simplifications here. X divided by x is 1. We have a double negative. Okay. So with this integration by parts formula, the integral we get on the other side of it is really not simpler than the original. In fact, it's like its cousin, right? If sine and cosine are cousins, you just get the cousin of the original integral. So it's not a simpler integral, but it's not more complicated. So we have to use integration by parts again. So using integration by parts on this sine log x, you would once again let u be the sine log x, because we know how to differentiate that. And dv is just dx, we definitely know how to anti-differentiate that. But so, just to be clear, in your lectures, you never heard the phrase cyclic integration by parts.
It is a term when you were explaining this, but yeah, we have their.
Okay. So they just use a different term. Okay, that's good. So. Okay, and then using integration by parts, u times d. Oops. And then integral of v du. All right. Okay, so let's put that together. Let's see. We have the original integral. And from the first use of integration by parts, minus, and then, or I should say plus, and then we used integration by parts on the sine of log x again. So we get x. And then minus our original integral. Right, and that's the that's what makes us cyclic, right? Where we started with our integral and using integration by parts twice, say we came up with our integral again, but now we can solve for it as if it were an unknown in an algebraic equation, right? Essentially, like this unknown integral is the business. Minus that same integral, so we can just add the integral to both sides. And notice I'm leaving off the constant of integration until the end. And then we get that our integral, after dividing by 2 on both sides, we get that our integral is this beautiful mess here. All divided by 2, and then you can add in our constant of integration. So that's an example of integration, cyclic integration by parts. And you might want to try something simple like e to the x times sine of x or something like that as well. You can use integration by parts on that, the cyclic integration by parts. Use it twice, you're going to get e to the x, integral of e to the x sine of x. Again, you can solve for it algebraically. I wonder what I'm missing for integration by parts. I don't think anything. Let's check what I did. It was number 6. Now this or this, actually. We'll try at home. Okay. Should we do this one? No, I don't think so. I'll just write it down so you can practice. Just move on. But this is an integration by parts. You'd have to use it twice. It's not cyclic. And you're going to get another integral that's log of x. And you would use integration by parts on that, right? If you have just the integral of log x, does anybody know what u and dv should be? Yeah, there's really no choice, right? We don't know how to anti-differentiate log x. I mean, that's why we're in this predicament in the first place. I guess log comes first in our acronym for choosing u. So why not? So you're just going to get u times v minus the antiderivative v du. So that's simple enough, but it's good to anticipate that that's a common one, right? And adding that log squared just makes you do integration by parts twice. Okay.
Question.
Yeah.
How can we look at an integral and decide that the cyclic method would work with this?
The cyclic method?
Yeah.
Oh, I don't know. I wouldn't.
Okay.
It's just experience. So they might say use cyclic integration by parts as a favor. I don't know, but for sure, I recognize that if you have like an exponential times the sine or cosine, that's cyclic integration by parts, because both kind of functions tend to reproduce themselves when you differentiate or anti-differentiate. I mean, not cosine, but you get its cousin sine. Okay. All right. Well, since we spent 42 minutes on integration by parts, I think that's enough. Do you guys have questions? All right, so the next topic would be integrals involving trig functions.
Someone has a question about integration by parts, I think.
Right. So this is going to be integrals involving trig functions. And you just want to kind of go through the cases. You know, you have cases where you have powers of sine and cosine. Just make it generic. Okay. And what are the possibilities, and will we account for all of them in this case? I think so. So you have where the power for sine, well, the power for sine doesn't matter in this case, but the power for cosine is odd. So, for example, you might have sine whatever to the power of 4, but the power for cosine is odd. What do we do in this case? Well, we definitely want to take advantage of the fact that the derivative of sine is cosine in a u sub. Okay. So we reserve one of the cosines. We just break off a factor of cosine and we reserve it for the derivative of sine. Right. So we're just going to save this. And then because the power for cosine started out being odd, and we took out a factor, the power for the remaining cosine is even now, right? And so you can start using trig identities, okay? So if the power for cosine is odd, we reserve a cosine, and then we use Pythagorean trig identities, okay? So we're going to use, of course, sine squared plus cosine squared is 1. Hence, cosine squared. So what you can do is you can rewrite the remaining cosine to the even power in terms of sine. So cosine squared now becomes 1 minus sine squared. And we still have this cosine over here. We're saving it. And this suggests a very natural substitution. We choose u to be the sine because the derivative of sine is cosine. So this will become sine to the 4, 1 minus sine squared. And this, of course, is just du. So you just end up with integrating a polynomial. Okay. And then we all know how to do this, so I'm just going to that's just integrating a polynomial in u. And then back substituting u is really sine. Okay. So that's one case. Yeah, the power for cosine is odd. And of course, you would do something very similar for the case. I'll just call it case 1, right? Where the power for sine is odd. The power for cosine doesn't matter in this case. Right, so now we just do almost the same thing, except we're going to reserve a factor of sine for the derivative of cosine. So we're going to end up with sine to an even power, cosine to some power, doesn't matter, and then we broke off a factor of sine. Okay. Now, because this power for sine is even, you get to use the Pythagorean trig identity, but this time we replace sine squared with 1 minus cosine squared. So I guess this was example 8, so I'll do example 9 next. You know what? You don't even have to have the cosine in the numerator, so let's do something like square root of cosine x, and then sine cubed, just for kicks. Because it's the same idea, we have an odd power of sine. We're just going to break off this factor, save it for later. And now that we have cosine squared, or in general some power, even power of sine, we can use our Pythagorean trig identity to rewrite the sine squared as 1 minus cosine squared. And we anticipate, you know, we're calculus students, so we know to write roots as fractional powers. And now we do our substitution, and we're going to end up integrating, I think u is cosine. Oops, I forgot the sign. Forgot to write down this sign. Okay, but I hope it's now makes sense that we should let u be the cosine and don't mess up in the sign when you differentiate cosine. Okay. All right, so 1 minus u squared, u to the half, and then becomes negative du. All those signs are terrible. So u squared minus 1. And of course, we only have one term in the denominator, so we just write this as divide the two terms in the numerator by that one term in the denominator and simplify. So you get u to the 3/2 minus u to the negative half du. And that's just a straightforward power rule for antiderivatives. And whatever this mess is, it is what it is. Back substitute. Okay, so that's the antiderivative for case 2 with a power for sine is odd. And what's case 3? So that would be where both powers for sine and cosine are even, right? So you get like sine to an even power, cosine to an even power. So even. Okay. So we already mentioned this, but in those cases, you just have to apply, possibly many times, your power reducing identities. Right, the reducing identities for sine and cosine squared are conjugates of one another. So, okay. Do you want to go through an example where we have that happening? So it might be something like sine squared, right? This is easy. Cosine squared, or you might have something like sine to the power 4, right? Or cosine to the power 4. Or forbid cosine to the power 6. I don't think they would do that to you, but in all these cases, you can just use these identities over and over. Did you want to do any of these? Well, not this one. Did you want to do one of these 2 examples? No? All right. You're pointing your finger to the second one.
Okay.
Yeah. All right. So this is 10. All right. So this is sine to the power 4. If I wanted to be mean, I would do something like, it's not mean, it's just there's some extra baggage you got to carry along, like sine of to the 4 5x. Maybe we should do that just in case. I don't want you to think that it's all sine of x and cosine of x, right? Right, but of course, so here, the power for cosine is even in the sense that you can think of it as a 0. It doesn't matter. You have an even sine to an even power. So we're going to think of that as sine squared, quantity squared, because we need to use the power reducing identity, which works for sine squared. So inside these brackets, we would use our power reducing identity for sine squared. Okay, and it's you double the angle, right? So you reduce the power, but you have to double the angle, so 5x becomes 10x. Okay. So what do you think we have to do next? Yeah, just go ahead and FOIL that stuff out, multiply it out, and we get a half times a half, and then minus a half cosine 10x, and a quarter of cosine squared 10x. After squaring the business the correct way. Okay, so of course the integrals of the first 2 terms are simple. right? We just integrate the 1/4 and then the 1/2 cosine 10x. But when we integrate the 1/4 cosine squared, what do we need to use? That's right. It's an even power of cosine. So we're going to use the power reducing identity for cosine squared once again. So let's just go ahead and anti-differentiate the first two terms. And then use the power reducing identity for the first and the third integral. So 1/2 plus 1/2 cosine, double the angle. So it was 10x, now it's 20x. Okay. And I guess I could plus c. And if we'd like, we could simplify that by distributing and all that and combining the sines and the cosines. I guess we could do that. We got 1/4 and 1/8. And then, well, we can't combine these signs, right? Because they have different arguments. So we would just leave it like that. So we have those three cases where you have sine times cosine. Would there be a fourth case, you think? Like, I mean, I don't think so, but you can tell me why. So what if we didn't talk about the case where the powers for sine and cosine are both odd, the powers are both odd, but why is that not really a different case? Like, so why is this not really a different case from the previous ones? Well, because if both powers are odd, that's covered by either case 1 or 2. Okay, so you can just choose one of these. I would probably choose the sine here because it's the lower power. We have our choice. The power for sine and cosine are both odd. I'll just use sine. And then you would rewrite the sine squared that you have remaining using Pythagorean trig identity. Right, sine squared is 1 minus cosine squared. And then you would use a u sub. I just wanted to point that out. I'm not going to do it. I'm just going to point that out. Okay. So maybe I should do an example where, yeah, let's do that before we talk about secant and tangent. Well, this is an interesting one, I guess. It even has bounds of integration. So I see a couple options here, but so the idea here is that it's hard to integrate trig functions if the like sine and cosine when the arguments are different, right? So we have some identities We already looked at the power reducing identities. I guess we should also recall that 2 times sine theta cosine theta, sine of double the angle. And I guess cosine double the angle can be thought of as cosine squared minus sine squared. So there's some extra identities we can use. Okay. I'm trying to decide what identity to use here. I think it would be easiest to use the power reducing identity on this guy, on the sine squared. Right, because if you reduce the power, remember the trade-off, you double the angle. So you would have to double 3x to get 6x, and then both trig functions would have the same argument. And then we're going somewhere, I guess. So we'll use power reducing identity for the sine squared. You get half minus half cosine double the angle, so 6x. And then we would have to distribute. All right, and we can definitely anti-differentiate the first term. Did you guys get a review apparently from the professors? Really? Okay. You did? No? Somebody's nodding yes, somebody's nodding no, but okay. All right. Can we anti-differentiate the first term here? Yeah, it's a basic trig function, so antiderivative of cosine is sine, and but can we anti-differentiate the second term? No. You know what? Let me just save the bounds of integration for later. So yeah, for the second integral, you have to use power reducing identity. And so this is actually a pretty cool problem. This time it's for cosine squared. Remember, you double the angle, cosine of double the angle. All right, anyway, and then you can anti-differentiate. So you get a fourth 48. And then I guess we can plug in the bounds of integration. Yeah. All right, so at the upper bound, what do we get? Sine of pi over 2 is 1. And sine of pi is 0, so okay, that's nice. So that's at the upper bound, and at the lower bound, everything is 0. I like it. Okay. But here we took advantage of the fact that like 6x was double 3x, and we can use, when we use the power reducing identity, double the angle. Does anybody remember what happens when you have like sine say 3x, and then let's say cosine of 7x. Right, where we're trying to get these arguments are not the same, but there is some trig identities we can use. Just scroll down to them. Just hope I can find them. One second. Ah, there it is. So we might tell you like, so when the arguments of your sine and cosine are both like completely different, we can always resort to these identities. And you would have to tell me whether you're expected to memorize these or no. I sure hope not. But I've seen them given before in exams. So you see how that's going to work, right? We have a product of two trig functions. The arguments are different. There's no quick way to get the arguments to be the same, so we just use these identities via brute force. So we're going to have sine of 3x, so a is 3x, cosine of 7x. Right? So a minus b would be negative 4x. A plus b would be 11 or 10x, sorry. Okay, so now we can write this as half sine of minus 4x plus sine of 10x. Why did I keep writing 11? Now we can integrate each term separately. And by the way, sine of minus 4x, how do you simplify? Not that I need to, but can you rewrite that somehow? Like sine of minus an angle is the same as the negative sine of that angle, if you want. Sine is an odd function, so we can just say that's minus sine. So we're just going to integrate term by term, and these are simple enough integrals. So you might, they might ask you to use these identities. Okay. So There's also the issue of secant and tangent, right? We have similar rules for secant and tangent like we had for sine and cosine. Okay. Okay, so case one for secant and tangent is where the power for secant is even. So these are a little different. Now, we want to take advantage of the fact that the derivative of tangent is secant squared. And also the Pythagorean trig identity, or the corollary to it, right after you divide both sides by cosine squared. You would get tangent squared plus 1 is secant squared. So we have the secant and tangent are somehow related by a derivative and also by one of the Pythagorean trig identities. And that's what we're going to be taking advantage of. So if the power for secant is even, let's do an example. Yeah, this is good enough. Let's use theta. Right? Secant has an even power. So we're going to break off a secant squared. The factor of secant squared. And what are we saving it for, do you think? What are we reserving the secant squared for? Yeah, the derivative of tangent, right? And a u sub. Okay. And the power started off being for secant being even, and we took out a secant squared, so this is still even. So we can use our Pythagorean trig identity relating sine secant squared and tangent squared. So we're going to think of secant squared as, or sorry, secant to the fourth as secant squared, quantity squared. Okay, and then apply Pythagorean trig identity where secant squared is tangent squared plus 1. And so we're just prepping this for a substitution where we see tangent and we see the derivative of tangent in secant squared. So that's u sub. And you just get a rational function there. And I guess we can just multiply the business out and divide by that single term, u squared in the denominator. And we know how to anti-differentiate each one of these. Simple enough. U is really tangent. Right, so that's when the power for secant is even, when you have secant and tangent in the integral. So I guess the next case, case 2, would be where the power for tangent is, well, you can tell me. What example was this? 13. I'm just numbering these for my sake. Okay, another case. Maybe let me just trigger your memory. So I guess secant cubed and maybe tangent cubed. Right, so the case I'm talking about, well, that's just an example of that case, but that's when the power for secant is tangent is odd. So it's the power for secant can be whatever, but the power for tangent is odd. And so here, the previous case, we took the advantage of the fact that the derivative of tangent is secant squared. Here, instead, we're going to take advantage of the fact that the derivative of secant is secant times tangent. And also our Pythagorean trig identity, or one of its manifestations there. So we're going to take advantage of these two facts. Okay. So to take advantage of the fact that the derivative of secant is secant times tangent, we're going to need to reserve a secant times tangent. Right, you need to break that off and just put it to the side, so to speak. So we're going to factor a secant and a tangent. The original power for secant is cubed, so now it's secant squared. The original power for tangent is cubed, so now it's tangent squared. And since this is the derivative of secant, we need to have our the rest of it all in terms of secant. We can do that via our Pythagorean trig identity, where tangent squared is secant squared minus 1. Tangent squared is secant squared minus 1. All right, now we do the substitution that we anticipate. U is secant. So our integral becomes secant squared minus 1, and then this is du. So that's a polynomial that we know how to integrate. All right. Oh, I guess in all other cases, if you're not sure what to do, you can always think about rewriting everything in terms of sine and cosine if you're not sure what to do. I can bring my example for that, so look it up. Well, oh, by the way, I guess we should review two integrals that we need. What is the antiderivative of secant? Yeah, very good. So you probably want to know that one. You can derive it if you'd like for practice, but you can derive it by multiplying the top and bottom by secant plus tangent. So that's not an obvious trick, right? Something that somebody would show you. Okay. But otherwise, just memorize it. Okay. And what is the antiderivative of secant squared? Yeah, the derivative of tangent is secant squared. Tangent to the power 4. Okay, so how would you integrate, just really quickly, tangent squared?
Trig identities, trying to secant theta dimensions.
Yeah, well, yeah, we know the antiderivative of secant squared. I guess we don't know or have memorized the antiderivative of tangent squared, but we know that we can express tangent squared as secant squared minus 1. Again, using Pythagorean trig identity here, right? So now we just, you know, the antiderivative of secant squared, then minus the antiderivative of 1 is just theta. Okay. Okay, so how would you go about anti-differentiating tangent cubed?
And the tan squared and
I don't know if I heard you, but
Like split it up into tan squared, theta, and then tan.
yeah. All right. And why did you want to do that?
So that you can do the substitution for secant squared minus 1.
So replace tangent squared with secant squared minus 1. And we're just using Pythagorean trig identity on that. Okay. And then we probably split this up into two separate integrals, right? The first one we do via u sub, where u is tangent, d would be secant squared d theta. And how do you do the second integral? Like, how do you integrate tangent of theta? Yeah, of course, this is, if you're, you know, sometimes I just rewrite everything in terms of sine and cosine if I'm not sure how to proceed, because I'm more familiar with those. But this integral here suggests a substitution where you use cosine. So du would be negative sine. So you'll get minus du over u. So that becomes minus and negative is plus, and then you get log of u. In this case, but yeah, because of the minus in general, it would be, let's just write it out. This is log of secant theta. Okay. What happened here is that there's a minus, and there's a minus here. You can use properties of logs to rewrite this as log of absolute value of cosine to the negative 1 power, which of course the reciprocal of cosine is secant. So you could have definitely rewritten this so that you can see the familiar antiderivative of tangent. Antiderivative of tangent is a log of secant up to a constant of integration. Okay. All right. I think we should move on to the next topic. It's been an hour and a half. Any questions about integrals involving trig functions?
What do you do when tangents is and secant is on?
Right, that's a natural good question, which I was not addressing. Trig sub. Do you remember the cases? So this is where you have a root and then you have two terms inside the root. Let me start with this simplest one. You have those three cases. And the idea is to take advantage of trig, right, to combine those two terms into a single term so that we can take a square root. So in the first case, what should we let u equal or try letting u equal? Starting with the Pythagorean trig identity, this reminds me of some constant squared minus sine squared, right? So we should let u equal a times sine. Okay. And then we would take advantage of the identity, Pythagorean trig identity. This will allow us to replace a squared minus u squared with a squared cosine squared. Case 2, so that would remind me of you have u as like your variable part, and then you have your minus constant squared, so we should let u equal a times secant theta, and then use the identity. And finally, the last one is really looks like this. You have a variable par squared plus constant squared, so we should let the variable be a times tangent of theta. And use our Pythagorean trig identity. Okay. So those are the three cases. Okay, so I guess let's do the first one. So the example of the first case, this would be problem number 13. Should be simple enough. We'll even put bounds on it. Okay, so according to those three cases, what should x equal in our substitution, trig substitution? It looks like the first case, right? You have 9 minus x squared is like constant squared minus variable squared. So it looks like the first case. So x should be 3 times sine theta. And then we complete the substitution. Of course, we need to compute the differential, I should say, maybe as a note, just don't forget the differential. And here we can either, right, there's two schools of thought here about the bounds. We can ignore them or we can change them, right? If we ignore them, what we're saying is we're just considering the antiderivative here without the bounds. We'll also change them as well, just to see. Okay. So I'm just considering the antiderivative of that. And we do a straight up direct substitution. X is 3 sine. So x squared becomes 9 sine squared. Okay, and then we also, of course, need to replace dx. So that becomes 3 cosine theta, d theta. Okay. And then hopefully this simplifies. By design, what does the numerator look like? Well, by design, we should have the same constant, 9 over here. So we can factor that out. And then we're left with 1 minus sine squared. So that allows us to replace the 1 minus sine squared with cosine squared. And then by the choice of theta, when we take the square root, you can just take the positive version of cosine. And then we end up with 3 cubed cosine cubed. And the denominator, and that indeed simplifies to 1/9 integral of 1 over cosine squared. And what's another name for 1 over cosine squared? Secant squared. So we get tangent. All right. All right, so what we have so far, by ignoring the bounds of integration, we found that our antiderivative is 1/9 of tangent of theta. And if we want to have our antiderivative in terms of the original variable x, what can we do? Did they teach you to draw a right triangle, perhaps? Okay. So maybe up here, if you want the antiderivative in terms of the original variable, just remember that you use the original substitution, use it to draw a right triangle as an aid. Right, label one of the angles theta, and we see sine of theta is u over a. So sine is opposite to ratio of opposite to hypotenuse side. Complete the third side using Pythagorean identity. And then drawing that right triangle, you can read off the trig function of theta, right? Whatever the trig function is. So if I want the answer in terms of x, I go back to the original substitution there, and I think of that as saying sine theta is x divided by 3. In a right triangle, x can be considered the opposite side, angle theta, and 3 can be considered the hypotenuse. The sine is opposite over hypotenuse. And then we use Pythagorean theorem to get the third side. And now we can easily read off what tangent of theta is. Tangent of theta is opposite over adjacent. So yeah. Okay, and that would be our antiderivative. But if we have bounds, since we found the antiderivative, we can now just plug in the bounds. Right, we found the antiderivative. And now we have, in terms of x, so we can plug in the original x bounds. It's there, it looks awful. Oops, minus. And at the lower bound we get 0. So I believe this simplifies to 1/9. Okay. Okay, so what's the other school of thought? The other school of thought says change the bounds, right? Okay. From x to theta, and then just use those. So let me. So we found that this is after the substitution, we follow this along and we get 1/9 of tangent. Oh, let me just write it. Well, whatever, this is our substitution. But at that point over here, we would change the bounds, right? Okay. All right. So we said that x is 3 times sine theta in the substitution. Okay. So then we reason when x is 0, what would theta be? Well, sine of 0 is 0, and that's the correct range for theta. So theta would have to be 0. So the theta bound here is theta starts at 0. And then when x is the upper bound, right? Let me write it this way. And we know that x is 3 sine theta. That doesn't make sense, does it? Oh, I miswrote it. The upper bound is 3 over root 2. So then we can, I guess, rewrite that. So we would reason that sine of theta is equal to square root of 2 over 2 if theta is pi over 4, where theta is in that appropriate range. Okay. So we change the bounds from x values, because it's an integral with respect to x, to theta values, because it's an integral with respect to theta. Okay. And then we would anti-differentiate, and we already know we would get tangent to theta. We did that work. And then you can just plug in these bounds. Pi over 4, and then we get tangent of 0. Tangent of pi over 4, I believe, is 1, right? Tangent of 0 is 0. So luckily, we get the same answer numerically. Okay. Okay, so that was the case. All right. Case number 2. Yeah, we could do that. Something like, let's actually do this. Let's make something up. Just to be clear about something. Okay. So this is the second case, I believe, right? Where you have a variable part squared minus a constant squared. Okay. So what do you think we should, in that case, what was the substitution? Secant, right? So what do you think we should let x equal? So the trick here is if the x part is being multiplied by a constant as well, you want to think of that as something squared, right? So where we identify u as the 2x and a as the 4. And what did we say in this case? U should equal? U should equal to a times secant theta. Just a heads up there. You need to think of the first term that has the variable part as some whole quantity squared and identify that as u. So that way u, which is 2x, is equal to a, which is 4 times secant theta. So then we can solve for x and we see x should be 2 times secant theta. I mean, yeah, the constant for in our substitution should be something that you'll get 16 secant squared minus 16. That way you can factor out that constant that's common, and then use your Pythagorean or your identity there. Anyway, okay, we got our substitution. X equals 2 times secant theta. Compute differential. And then directly substitute. Underneath the square root, we get 16 tangent squared. Denominator is x, so 2 times secant, and dx we know as well. And, oh yeah, okay, we do, okay, cool. So we can simplify a bit. And this theta business, right, is just these are variables of convenience here. So we choose them, so when you take the square root of tangent squared, we know in general what this should be, right? In general, it should be the absolute value of tangent. But by choice of range for theta, we chose theta so that we just use the positive version of tangent. So you don't have to worry about square root of something squared being its absolute value for the strict sub. And then we get our old friend here, tangent squared, which we said you can integrate by rewriting tangent squared as secant squared minus 1. And then doing two separate integrals because we know the antiderivative of secant is tangent, or we know the antiderivative of secant squared is tangent. All right, and that's it's an example of an indefinite integral. So we probably want to write the answer in terms of the original variable x towards that end. We use our original trig substitution. Secant theta is x over 2. So I guess since cosine is adjacent over hypotenuse, secant would be hypotenuse over adjacent. So we can consider the x as the hypotenuse and 2 as the adjacent side relative to theta. Awesome. So now we see that secant of theta, according to our right triangle, is opposite side over adjacent. And theta is theta, right? What can we do with theta here? How do we write theta in terms of x? Sorry, just arc secant. Up to it. Okay. Yeah.
Let's say, not for this question specifically, but for some integral, we got the answer as 4(2 theta or 4(3 theta.
Oh, that's a great question. Thank you.
How would you write that in terms of x?
So the question is really good. So, like, what if you had in your substitutions? This is just a random example. Is like x over 5 or something, right? So x was 5 sine theta, and your antiderivative, whatever the integral was, let's say you got sine of 2 theta. Maybe let's do cosine of 2 theta, something like that. How would you deal with that is the question.
Yes.
So trig identities. So sine of 2 theta is equivalent to, you want the original angle theta, right? So we know that sine of 2 theta is 2 times sine theta cosine theta. So that way you can rewrite it. I have a feeling you knew that, and you're just prompting me to make sure everybody else hears it. So that's good. Okay. And then what about cosine 2 theta? All right, we can use that identity. And so now we have sine and cosine of theta, and we can use that tool, that aid, draw a right triangle, complete the sides, and then read off the trig functions like sine of theta. Well, we know what that is. But cosine of theta would be adjacent over hypotenuse. All right. So cosine squared and sine squared. Okay, awesome. That was a very good reminder. Thank you. All right, and the last case, problem 16. Right, so this is the plus case here. So we said for that, you just let u equal a tangent theta in order to take advantage of the identity. One plus tangent squared is secant squared. Okay. So here x, well, u is x, right? And a happens to be 3. So you get x, 3 tangent. Yeah. Plug and play there, direct substitution. It's x squared. We know that this will become, what does that become? 3 secant. And dx, don't forget dx is 3 secant squared. What kind of integral do we get here? Secant theta and then tangent squared. I guess I would just probably write everything in terms of sine and cosine. I think that works. Right, we get our secant is 1 over cosine, and tangent squared is sine squared over cosine squared. So unlike the previous example we tried, this actually is, you can just use a u sub here. Right, in our u sub, we let u equal sine theta because we see the derivative of sine there. So that becomes okay. So what is u sine? Okay. So it looks like it's a negative 1/9 of cosecant theta. I don't see any bounds, so I guess we should write our answer in terms of x. So we said x is 3 tangent, so tangent theta must be x over 3. Tangent is opposite over adjacent. Okay, so cosecant, it looks like, would be hypotenuse over opposite. That's pretty good. Okay. Trying to think if we had bounds, what kind of problem would we use? Probably have an improper integral, right? If you go from 3 to infinity. Tangent. So if we were to change bounds, right? So we would do the same trig sub, and it's still going to be improper integral because of this. Right, but we would end up with some integral, but what would the bounds be in terms of theta if you had to change them to theta? Remember that the substitution we're using here is x equals 3 tangent theta. Okay, so when x is 3, we would have to figure out that tangent must be 1, which we're going to assume that theta is pi over 4. And when x goes to infinity, so this is an abusive notation, of course. When does tangent go to infinity? And that's really in quotes, it's really a limiting thing. When does tangent go to infinity? When theta goes to pi over 2. All right. So we could try it that way, but that would be the next section, right? It's the improper integrals. Okay. So the next one I'll skip because I think 3 hours is a little long. So maybe we can go on to improper integrals, but I'm just going to write down the answer if you want to practice. Maybe changing bounds as well. But numerically, this is square root of 2 minus 1. Okay. So I think that's enough for trig sub. Oh, there's more. There's some partial fractions. Okay. You'll have to learn a lot. I feel sorry for y'all. A lot of work. So I think the next thing we'll do is partial fractions. So what's a rational function, by the way? It's just polynomial divided by polynomial, right? And sometimes we get complicated rational functions, and hopefully we can rewrite them as the sum of simple rational functions. The process by which we do that is called partial fraction decomposition. Okay, so I guess some notes. So first of all, you have a polynomial on top and bottom. That's a rational function. These are polys. To use partial fraction decomposition, we have to have that the degree on top is strictly smaller than the degree on bottom. And then you can use partial fraction decomposition. PFD, right? All right. So if it's not, right, if the degree on top is as large or bigger than the degree on bottom, then what do you first do? Use long division first. And then you're going to end up using partial fraction decomposition. All right. I guess third point would be the form. You'd factor the denominator if it's not factored for you already. If you're going to use partial fraction decomposition. Okay. And let's just recall the form and assume the form that our partial decomposition takes. So we have some polynomial on top. And let's suppose we factored the denominator. Let's do this. X minus 1, x plus 2 cubed. Okay, that's it for now. Okay, so these are considered linear factors. Okay. This is a linear factor of multiplicity 1, because the power for that factor is 1. Oops. And x plus 2 is a linear factor that has multiplicity 3, because of this cubed for that factor. And then we have x squared plus 5, which is considered a irreducible quadratic factor. It's irreducible in the real numbers, right? This is a quadratic factor. Is it reducible or irreducible? X squared minus 4. It's reducible. In other words, we can just, instead of thinking of it as a quadratic, we just think of it as factored into two linear factors. Okay. All right. So we write down separate fractions where our fractions have the factors here. So you have a linear factor. And then you also write down the factors up to the multiplicity. So x plus 2 has multiplicity 2. 3 rather. Because there's a cube, so you'd write out all three. X plus 2, x plus 2 squared, and x plus 2 cubed. And then we have our reducible quadratic factor. So if you're dealing with the linear factors, you just put a degree, polynomial of 1 degree less. So if you have a linear factor, you just put a constant. Even if you're doing the multiplicity business there. But if you have a irreducible quadratic factor, you put 1 degree less on top. So that would be a linear factor. Okay, so that's just a reminder, correct, of and what if we had, doesn't matter. Let's say x squared plus 5 squared, so that irreducible quadratic factor has a multiplicity 2. Well, again, you just write out the factors all the way through the multiplicity. So x squared plus 5 has a multiplicity 2. And you just put, if it's a linear factor, you just a constant on top. If it's a reducible quadratic factor, it's a linear factor on top. Just as a reminder of the starting form that you need to assume. Okay. And then you multiply through by the common denominator and try to solve for a through whatever. Okay. So let's just do some examples. That was just an outline, I guess. Okay, let's start with an example. be 18. Okay, so we have polynomial divided by polynomial. Can we go ahead and use partial fraction decomposition now, or do we have to use long division? Yeah. We can go ahead and use long division, but the degree on top is 3. It's the highest power of x. The degree on bottom is 4. So the degree on top is smaller, strictly less than the degree on bottom. We can go ahead and use partial fraction decomposition to write this as, we write this as a sum of simpler rational functions. We first factor the denominator. So apparently we can just factor out an x squared. Okay. All right, so that x squared, how are we going to think of it? Like a linear factor or an irreducible quadratic factor? We're going to think of it as a linear factor. So, and it has multiplicity too. So you'd write x and then x squared, and then constant on top. And this is irreducible quadratic factor. So multiplicity 1, so we're just going to have a polynomial, I'm sorry, a linear factor on top. Okay. All right. So I guess the next step after you decide the form for your partial fraction decomposition, I would just multiply through by this common denominator just to get rid of it in one fell swoop. So this is going to be an abusive notation. I'm going to multiply both sides by the common denominator to get rid of it. All right, so I guess, yeah, the x squared is going to cancel one of the x's there. And I guess our x squared is going to cancel the x squared over here. So we're left with and I think this x squared plus 2 is going to cancel the x squared plus 2 for the last term. So we're just left with an x squared. Okay. Kind of just as a quick practice thing, if I wanted to know what b is really quickly, what could I let x equal if I needed to know what b is right away? Yeah, right. So the idea is that these two sides are equal polynomials, and they're equal if they're equal for all possible x's, including specific values of x. So one strategy we'll see is just to choose x to be certain values. Like if you let x equal 0, somebody's recommended we chose it to be 0 because you see a bunch of factors of x, which will zero stuff out. So if x is 0, the left-hand side here would be 2, and the right-hand side would be, 2b. So b must be equal to 1. Okay, but here, because we have x squared quadratic terms, I'm just going to use the other method. So what's the other method? It's just to multiply everything out. And then say that polynomials are equal if and only if like the corresponding coefficients on either side agree. So this method, you just multiply everything out. And then combine like terms, so you got your cubed terms. You have your square terms. And you have your x term. There we go. And then your constant. On the left-hand side, if you'd like, there's a 0 times x squared, 0 times x. Okay. So yeah, for these things to be equal, the coefficient for x cubed on either sides have to agree. The coefficients for the x squared terms have to agree, and so on. And hopefully, since the linear algebra is not a prerequisite here, it should be easy enough to solve in your class, I hope. So we know that a equals 0. And if a is 0, then c has to be equal to 2. Clearly, b is 1. So that d has to be negative 1. Okay. So we figured all these out. Okay. So a is 0. So that first term goes away. B is 1. C is 2. And D is negative 1. Awesome. Okay. So now our original integral is the integral of the simpler rational functions. Okay, and we can integrate term by term. So, okay, we can integrate 1 over x squared, no problem. But what do we do as a second term over here? What do we have to do to it? Split it, right? Because we recognize like 2x over x squared plus 2, you can use a u sub. And the other one would give us some sort of arctangent. So to split it into 2 separate terms and integrals. Okay. So the first antiderivative is simple enough. The second one is a u sub. You let u equal x squared plus 2. So that will give you log of x squared plus 2. And I guess we should recall that formula, right? So what's this antiderivative without using trig sub? And if you did, what would x be? What's that antiderivative in red? Okay. All right. Well, so 1 over a, arctangent, or inverse tangent, I guess, x over a. So that one you kind of want to know. You can rederive it for practice using trig substitution, where you let x equal a tangent theta to see if that's correct or not. All right, so our integral over here is of that form, except we have to think of this 2 as the square root of 2 squared. So we would get 1 over square root of 2 arctangent x over square root of 2.
For the first fraction of the answer, would it be negative 1 over x?
Oh yeah, it is. No, thank you. So over here, I forgot. I was doing the antiderivative, and I looked back to check, and I just wrote down x squared. So, yeah, thank you. Okay, so let's do another one. All right, so are we ready for partial fractions here? Or should we do something else, right? So the degree on top, I'll just write top polynomial, right? Is 3. The degree on bottom is 3. So the degree on top is not strictly less than the degree on bottom. So we're gonna have to use long division first. Just division. I'm not sure it's called long division. What's short division? Has anybody seen the short division algorithm? Okay. All right, so let's see, 2x cubed divided, so we're just, of course, considering the highest power terms. So I guess x cubed goes into 2 times x cubed twice, so that'll be the end of that. And then multiply through. Let's be cheeky. All right, subtract. And we're done, right? Because this is now degree 1, and all this was 3. So after the division, the quotient is 2. Then we have plus the remainder divided by the original divisor. Okay. So now we're ready to apply partial fraction decomposition to this. The degree on top is 1, the degree on bottom is 3. So let's just do that. So I guess step 1 would be to factor the denominator if it's not done for you. Oops. So I see 3 linear factors. One of them has a multiplicity of 2. The other one has a multiplicity of 1. Okay. No, I guess nothing in the loop. So now multiply both sides by the common denominator. And here, instead of multiplying things out, I'm just going to use that technique of just saying, well, these should equal for all x's, so I could let x equal something specific, like x equals 0, for example. We'll get that b is equal to 3. Is that correct? Yeah, right? All right, well. And then we could also let x equal, what other value of x would zero stuff out here? Since we have a factor of x plus 3, we should let x equal -3. So this becomes -9. This becomes c -3 squared, so c is -1. And then how can we quickly find a value for a? Well, we can just choose x to be anything other, right? Anything else. What do you want it to be? Let's say 1. Left side is 11. This is 4a, 4b. Let's see. B is 3, and c is -1. So a has to be 0. Nice. Okay. Let's hope I did that right. Okay. So we found that a is 0, b is 3. And c. Okay.
Because b equals 6.
You said b is 2.
B.
Where did I go wrong? Oh, because 6 divided by 3 is 2, not 3. Okay. So I need to adjust this. What do we get? Sorry about that. Mhm. To the 11, 4a, 4b, and c.
Also, one more question. Will this entire recording be uploaded to the YouTube peer review channel?
Okay, well, good enough. A is 1 then. I think that's right. Okay. A is 1, B is 2. Thanks for catching that. And then we can just integrate term by term. Cool. All right. Cool. Thank you. All right. I guess what other things should I look for? Partial fractions. There was something I'm trying to recall. Let me see if I have it. Just a common one that you might see. Yeah, all right. Just something like this, I guess. I've seen these often, so. Cool. So this is still partial fractions, right? I guess you could try using trig sub if you wanted to, but let's factor the denominator. I believe this is a difference of 2 squares. So this is like 2x squared minus 3 squared. And so that factors into a product of conjugates. So we get 2 linear factors. Okay, then we multiply by this common denominator. All right, so I guess just to be clear, right, when we multiply by that common denominator, you have to make sure you cancel the correct factor. Right, so when we multiply through to the term containing the a, the 2x minus 3's cancel. So you're left with the 2x plus 3. And okay, whatever. When you multiply through the b term containing the b, the 2x minus 3 cancel. So you're left with the 2x minus 3. All right. So I guess here I'm just going to multiply through, even though I could let easily x equal 3 halves and negative 3 halves if I wanted to. Great. So what does a plus b have to equal then? And what does a minus b have to equal? What does 2a plus 2b have to equal? Yeah, right, because there's no x term on the other side. You can think of it as 0 times x. And then the constant term, sorry, 3a minus b, is 1. Okay, so this tells us that a is the negative, or say b is the negative of a. And if b is the negative of a, so a would be 1/6. So b must be negative 1/6. Cool. So you get easy peasy, right? And so we get 1/6. We do a u sub, I guess, and to get a log. In the first one, we would let u equal 2x minus 3, and the second one, you let u equal 2x plus 3, and you would get logs out of that. Okay. So I think this would be a good problem if you had an improper integral, don't you think? Let's say integral from 4 to infinity. I'm just wondering why you see, like, why I think this would be a good improper integral problem. Well, I mean, we would set it up correctly. Of course, the improper bound is infinity there. So Well, we'll get into proper integrals next, right? Just the procedure. But how would you evaluate this as x goes to infinity? So if we have an improper bound, and again, I'm using notation, please don't do this. When we evaluate our antiderivative at the upper bound, it's really a limit as x goes to infinity, correct? So how would you evaluate that limit? Well, you'd probably take advantage of properties of logs. Log of a minus log of b is the same as log of the quotient of a to b. So we have a 1/12, which is a common factor, and then you get log of 2x minus 3, that's like our a, and then divided by 2x plus 3, that's like our b. And, I'm sorry, it's an abusive notation. It's really a limit. So as x goes to infinity, what's this limit? Write it out. So from proper integrals, you should probably be able to do this limit. So what is this limit? How would you evaluate it? Yeah, I mean, so yeah, you could. Log is a continuous function, so you can just find the limit of the inside, right? So you can just take the limit of the inside, and you can use L'Hopital's if you don't see that this is equal to 1, whatever that is. It's and so you can use L'Hopital's on the inside. Because if we evaluate directly, we get infinity over infinity, but using L'Hopital's, we just differentiate the top, then differentiate the bottom. And now we have the limit of a constant. So it's equal to that constant. The limit of 1 is 1. Anyway, so we get an answer. Does anybody know if this numerically is positive or negative? This is a numeric answer. Okay. It's positive, right? Okay. Did you guys complete the square as well? I think so. So one more. Or was it? Sure, why not? Now let's do x plus 5. That looks simpler. So can we use partial fraction decomposition here? We could, yeah, we could try, right? We would try to factor the denominator. Does anybody see an issue here with factoring the denominator? So if we find the roots of this quadratic, we can factor, right? And if we try to find the roots, we can use quadratic formula. The problem is there are no real solutions, right? You get complex roots, so. There are no real roots, so this is in fact an irreducible quadratic factor. So what do you do in that case? Does anybody recall? Well, we can complete the square in the denominator. So if you have, like, this is irreducible quadratic, and so is this. But here, I guess we have to complete the square. Let's see. So we're gonna half the coefficient for x. We're gonna square that, add that in, then subtract that number out. Right, so half the coefficient for x, you square it, that's what you add, and at the same time subtract. That way you're just adding 0, not changing anything. So complete the square sometimes. Okay. And if we do that, right, these terms by design should be a perfect square. And then you just lump the constants together. Okay, so how can we proceed here? Well, we can do a change of variable if you really wish, if you don't see it. If you do a change of variable, let's call this z. Let z equal x minus 1. Right, so that way dz is just dx. So that's one way to do this. What would z be? What is x then? X would be z plus 1. So you get x plus 5 becomes z plus 1 plus 5. And then we have z squared plus 4, if this is the way you want to do it. And then you can split this up into two separate integrals, both of which you know how to do via either a substitution or you get an arctangent. Okay. I was just going to use that old kind of sleight of hand where I see an x minus 1, so that's exactly what I want to see in the numerator. So I subtract 1 and add 1, thus adding 0, not changing anything in the numerator. And then, you get your x minus 1 plus 6 over. And then you can split this up into 2. So maybe, I don't know which one is more manageable. You get the same integral. So I'll just do it the way we did it in red. Okay. All right, so using a u sub, this gives us half of a log z squared plus 4. And this gives us 6 times. And then arctangent, right? So the antiderivative would be 1/2 arctangent z over 2. Cool. And unfortunately, then you have to back substitute. So. All right. So if you get a irreducible quadratic, sometimes you complete the square and do a substitution. Okay. So finally, we can just talk a little bit about improper integrals. So how can an integral be improper? There's like 2 different ways, right? What are the 2 different ways? Okay, so I guess why is this integral improper? As soon as you have a bound, which is infinity or minus infinity, we have an improper integral. So a bound, it's infinity or minus infinity is automatically improper because it's infinities invite limiting statements, right? Proper. And what about this integral? It's an improper integral. Can you tell me why?
Eventually rounded to 0.
Yeah.
Well, it's something else.
Yeah, because if one of the bounds, right, if there's a value of x on the interval of integration, which makes the function gives the function a vertical asymptote, or say 0 in the denominator, if you will. Okay, then it's improper. Right? So that's another way to be improper. There's some value of x in the interval of integration, which makes the function discontinuous, if you will, but really you get if you have a vertical asymptote. Discontinuous, or if you will, I guess. We'll just keep it that way. I'll just say discontinuous. Okay. And we only allow one improper thing per integral, correct? Right. So let's just. How do we set this up? If you have an improper bound, what do? Well, you remove it. Okay, so you're just going to do an integral from 1 to, and you just give it a letter name like b. So no, it's no longer improper because b is some unknown but finite number. And after we evaluate this finite integral, right, this definite integral, we're going to then take the limit as b goes to infinity. When is your exam? Is it Wednesday or Friday?
Friday.
Did you cover improper integrals? Oh, okay. All right, so if you have infinity or minus infinity for the bounds, it's improper, okay? You remove it just with a letter. We don't know what b is. And if I could just cover up that limit statement, you're going to evaluate this definite integral. And then after you compute it, you're going to then lastly take the limit as b goes to infinity. And if that limit exists, the integral is said to converge. Uh-oh. And if the limit doesn't exist, the integral diverges. Okay. So you have to, part of the setup is part of the grade. This is the very definition of an improper integral. It's really a limit of a definite integral. Okay. And then you would find the antiderivative. Does anybody know what the antiderivative of this is? If you just on the side to save time, so we don't have to write the bounds over and over. Consider the indefinite integral of e to the x over e to the 2x minus 1. Does anybody know what this is?
Natural log of e to the 2x minus 1?
I wish. Yeah, if it would be if it were something like this, right? Then it's no problem log, because if you let u be the denominator, du is just e to the x dx, so that's the numerator. So yeah, in that case, you'd get a log. But unfortunately, here we have e to the 2x. Okay, so right. So in that case, we just have to use a substitution, taking advantage of the fact that e to the 2x is the same as e to the x quantity squared. And also the fact that the derivative of e to the x is e to the x. So we would let u, I guess I need a sign-in sheet. guess for the body count of the bosses. Okay. Right, so you haven't been lectured over improper integrals. They can't get too deep over it in 2 lectures, right? Or maybe. I don't know how it works. But you let u equal e to the x so that du is e to the x. Right? Dx, sorry. So this is du. And this will become u. So you get. And this integral, I believe, or this is partial fractions, guys. Oy, oy, oy. I believe that would be so a half. I'm not going to make you go through the partial fractions, but here it is. That's why you guys didn't know what I was talking about previously. Okay. All right, so you get 1/2 log of u minus 1. U is really e to the x. Okay. So we found the antiderivative. Next, we're going to plug in the bounds of integration. So you plug in b. Seems kind of weird that you're replacing a letter with a letter, but you are. Minus at the lower bound, you get something, who cares? Some number, it's finite in any case. Now you take the limit as b goes to infinity. Okay. And if this limit exists, we say that the integral converges to that limit. If the limit doesn't, thank you. Then the integral diverges. All right, so on the side. Use L'Hopital's rule, I suppose. Bring the log is a continuous function. We can bring the limit statement inside the log. And if you need to, use L'Hopital's. But if you do, you're going to get 1 for that limit on the inside. I hope you see why that would be. So you get 0. All right, so the limit of that first term is 0 as b goes to infinity. And the limit of the second term, well, it does not involve b. It's a constant as far as b is concerned. So well, it is a constant because he's a number. So you just get that. So yeah, okay, that makes sense. So the answer would be, if you wish. Okay. So that limit exists, and it's equal to this. Therefore, our improper integral converges to that number. Now let's end it there. I didn't realize, I should have realized that you wouldn't have covered all of improper integrals. Maybe I should have done something simpler in that case. So the other way to be improper would be to have a value of x where your function, say, is discontinuous. Why not? Let's do that. Something like that. Very simple. So why is that integral improper? Well, at the upper bound, when x is 4, your integrand gets a denominator of 0, right? So that's a discontinuity because your integrand is not defined at 4. But it's the same setup. You replace the pesky improper bound with just a letter. And we're going to compute this definite integral. plug in the bounds, and then after we do that, we then take a limit as b goes to 4. With the slight nuance is that since we're integrating on the interval from 0 to 4, whatever b is, it has to be inside that interval. So b is going to approach 4 from the left. And then we consider that the antiderivative here. I think that's just a simple u sub. Oh, that's a pain though. Okay. All right, sorry if that's a little quick. Okay. All right, so now we plug in the bounds. And it's very likely they'll take off points if you don't like the limit statement, which is really annoying, right? Because it's like the first thing you write, but the last thing you actually end up doing here. It's a b. And what do we get at the lower bound when x is 0? Okay. All right, so now you plugged in the bounds with one of the bounds being just a unstated number, and you take the limit. And indeed, this limit exists. You get 0 minus 0, and then whatever this is, 30 and 1840 minus 16. Okay. But you get a finite number. So since that limit exists, we say that this improper integral converges to that number. If you get an infinite limit, it would diverge. But it's kind of late, so 1 to 4, yeah. I'll let your professor do the lecture. I won't do any lecture. And good luck. I'll see some of you all in the tutoring lab, I guess. Okay. And thanks for staying on, for the virtual people online. Thank you so much for being patient. I apologize that we didn't have our regular platform. And thank you, Aisha.